Hello, everyone. My name is Priyakshi. On behalf of EV Reporter and HBK World teams, I would like to thank you all for joining us for this webinar on advanced measurement solutions for electric powertrain and batteries. We are glad to have professionals across the EV ecosystem, including OEMs, powertrain and EV component companies, and battery solution providers joining us for this event. We hope today's technical presentations will provide you with valuable insights. So let me quickly walk you through the event agenda for the day. During the next hour, we will see two presentations. The first is by Mitch Marks, and it's dedicated to troubleshooting EMC and cabling issues for electric powertrains. And the second session will be led by Ranoji Khochare, who will be focused on fatigue analysis and reliability of EV components. After both presentations, we'll have a 10-minute Q&A session, and you can add your questions to the Q&A box on the bottom of the screen. So without any ado, let me first invite Mitch Marks. He is joining us from Tokyo today. Mitch is a business development manager at HBK World, and he has been working in electric motor development since 2015. He specializes in test and measurement of electric traction motors and drives, and he has been with HBK since 2017 as a member of the electric power testing team. Today, his session is focused on combating EMC issues for accurately measuring electric powertrains. Over to you, Mitch.
Excellent. Thank you so much to EV Reporter for letting us host this event, and I always appreciate the EV Reporter audience and team. So thank you so much for having HBK. As mentioned, this session is going to be largely focused around measuring EV powertrain, EV batteries, and some of the challenges that can be overcome. I'm Mitch Marks. I'm business development for the electrification products at HBK, and as mentioned, I'm based out of Tokyo. I'm going to start with an introduction to HBK very briefly, and then get into the things you're here to learn about. So HBK, Hottinger Brulin Care, is a test and measurement company. And HBK is really here for one purpose, and it's to help engineers make, validate, simulate designs. We really want to help you go from the design phase where you're coming up with a really brilliant idea and thinking that this brilliant idea is going to work, and allowing you to do that through software tools, through simulation, and then going to the real world and validating those real designs. So going from I think I can to I know I can, and really trusting the products that you're going to put out into the market. How do we do that? We really cover three main areas: research, development, production, and in product. And we make sensors, measurement systems, analysis software, and simulation tools to cover these three areas. Today's mostly going to be focused on the research and development area, where we have these really high accuracy sensors and measurement tools. But we also can support production, looking at making really high quality products going into the market, offering software for tracking those products, understanding fatigue life, durability life, reliability. And then we also offer in-product sensors. And these are really high accuracy sensors and measurement systems that are going to go into test stands, that are going to go into production lines, and that are even going to go into things like cars or aircraft for continuous monitoring. So again, we offer sensors, measurement tools, analysis software, and simulation. And maybe even more importantly, we have a lot of experts in the local markets to help you understand your problems. And hopefully we're going to achieve that today with this webinar. So getting to the main topic at hand, at least for me, before I hand over to Ranoji, overcoming EMC issues for accurately measuring electric powertrain. And I think this is going to be really interesting. We see a lot of customers, as they're bringing inverters into their lab, as they're bringing more modern, more high-tech inverters into their lab, having a lot of trouble with their measurement quality, having the challenge of, can I trust my measurement? So that's what I'm hoping to help you guys overcome today. And you feel free to reach out to me, Mitch Marks at hbkworld.com. There's also a Q&A session here where our team will do our best to answer your questions, and we're really good at getting back to people. So please send your questions. So what does HBK offer for measuring electric powertrain? We'll start with a little bit of the product before we get into the meat of the technical details. Well, we offer sensors, data acquisition, and software for measuring your motors and your inverters. We have torque sensors, current sensors, load cells, accelerometers. We have data acquisition systems where we can bring in all of the electric and the mechanical measurements into one place. And then we have software for looking at your measurements, looking at your results, plotting your efficiency to really understand what you're doing. And we like to think we do 5 things particularly well. We make it very easy to measure the electric and the mechanical signals in one place: temperature, torque, speed, voltage, current at a very high bandwidth. We make very fast and accurate efficiency measurements. If you want to look at your energy consumption through a drive cycle or very accurately measure your power, we can help you do that extremely quickly so you can accelerate your product development. We can expand to high channel counts. If you have a big monster, a complex system, we can make it very easy to make many measurements in one place. This could be if you have multiple motors in a vehicle, multiple inverters. Very simple to bring it into one place with those mechanical signals. We can record data for as long as you want. If you want to measure at 2 megasamples on 10 channels for 10 hours, please contact us. We're very good at that. We can record lots of data. And this data is going to be quite useful for understanding our measurement quality. It's going to be quite useful for understanding, is this a good measurement, which is the topic of today. And then we have real-time calculations and feedback. This allows you to, in discrete time, feedback to an automation system, go to hardware in the loop, or correlate to other measurement systems. And this presentation is going to feature some examples from our products. In short, we see ourselves as 5 things in one package. We are first and foremost data acquisition. We record really high quality, high accuracy data. That data has a very good time alignment, and we do those real-time equations so that we can give you an extremely high accuracy power measurement. So we are a data recorder and a power analyzer in one. We record measurements at up to 2 megasamples per second, and in the future, 20 megasamples per second, which gives you the ability to view your signals like a scope trace. You can view things happening live on the screen and have an intuition to your measurements. So now we're 3 things in one: data recorder, power analyzer, oscilloscope. We allow you to measure those mechanical signals, CAN bus, temperatures. So again, you can have everything in one place. And then we do have some really powerful analysis tools for doing efficiency mapping, or your DQ0, or phasers, or just looking at the power flow of your system. So that's what we offer. We offer a data recorder, power analyzer, this really powerful all-in-one tool. But today's topic is more the application of that and using it. So what we're going to go through, we're going to go through the electromagnetic interference background. For those of you who experience these issues but maybe don't understand them so much, we're going to go through a little background on EMI. We're going to look at these new technologies that engineers are sending our way, and we're going to look at how do we attack these challenges that these new technologies are giving us. We're going to understand why these new technologies are giving us challenges. We're going to go through some cabling best practices. I'm going to touch briefly on sample rates and filtering. I'm going to be very honest with you guys. I might have put too much here, so I'm going to go through this quickly. We will be sharing the presentation, so you can reference that. And then we're going to go through some new tools that HBK offers for overcoming these EMC issues. So a background, and I apologize for everybody who knows this very well, but for those who don't, EMI, electromagnetic interference, is electricity from one source interfering with a signal. And that's a pretty generic explanation, but for those of you who are over 30, this example will be good. Under 30, think of this instead of television as Wi-Fi. But if you are watching TV, watching television, and the screen starts to go all fuzzy because there was bad weather, because your mom or dad turned on a vacuum cleaner, or because there was a really old car with a spark plug not well isolated, your TV would get all fuzzy. And really simply put, that's what electromagnetic interference is. I'm receiving this signal on my television and it's being interrupted by something happening away from the TV. And that's the issue that we have in measurement. And if we look at it more as a circuit diagram and we get a little more academic, I have my sink of my interference, my television, and then I have my source of my interference. And these at some level are sharing a common circuit. Now that could be shared inductively. That could be shared by a galvanic connection, a physical connection between two places. It could be radiated, like weather, for example, is kind of radiating magnetism to our sink, to our television, or capacitively. And I'm going to go a little deeper on these, just so we have that kind of common understanding. If we turn my little more archaic circuit diagram into a real circuit diagram, we have something like this RA. This might be my measurement system. You know, I have signal wires receiving a measurement, and then I have my load. This could be my inverter or my motor. And I have a high power signal line. And my measurement line and my power line are often in quite close proximity. So we have, for example, galvanic interference, where this is actually a physical connection between my source and my sink of interference. This could be bad shielding. This could be grounding loops. This could be a variety of different things where the two systems are actually in contact. We have inductive-based interference, where I have a current carrier. This could be my inverter cables with their high frequency. And the high currents create a magnetic field. And this magnetic field can get picked up by my measurement cable. And this is going to induce a voltage. And here we have dependencies of frequency. We have dependencies of current. We have dependencies of distance between the two cables. We effectively end up with this function di dt, the change in current over the change in time. We have capacitive coupling. This is very similar to my inductive, except now I have two cables that have a capacitance between them. And I have charge from one cable jumping over to my other cable, my measurement cable. This has dependencies of frequency, voltage level, again, distance between the cables. And this gives a function dV dt, change in voltage over the change in time. So we see some trends when we start talking about inverters. We have high currents, we have high voltages, we have fast frequencies, and then there's electromagnetic radiation, which is this more long distance. This is the magnetic field and the electric field interacting with one another. And this is a function of distance. It's a function of di dt, it's a function of dV dt. So we really have these kind of key elements here. And we're going to go a little further on these as well. So what affects electrical interference? Well, it's the voltage level, dV dt, the current level, di dt, the frequency, this affects both di dt and dV dt. Parallel paths. If these two cables are running in parallel, they have a longer surface area between them. They have more area to increase the coupling. The distance between the cables, this matters. If the cables are right next to each other, that will increase the coupling. And shielding, bad shielding or bad grounding can create ground loops. And we keep coming to these effects of induced current on my measurement line is an equation C dV dt. Induced voltage, and these are my electromagnetic interference equations. My induced voltage is inductance times the change in current over the change in time. So these are kind of the equations we have to think about when we're thinking about electric noise. How do I mitigate these two equations? And I'm going to come to this at the end, but I think the question I have for you guys is, how do I eliminate copper paths? And we'll come back to that. Just think about that for a little bit. So getting to the practical. Nobody has ever had a measurement lab where somebody brought in equipment and set it up and it looked like this, where we have loops of cable, where we have a high voltage inverter right next to my measurements, where I have equipment stacked on top of each other, creating ground loops, high voltages everywhere. This type of setup results in very poor measurements. And this is what I'm hoping to help you guys overcome today. Anybody can look at this and say, this is bad, but there's some subtle things that you might miss. Even in a good setup. So what are the new issues? I've got great cabling today. What are the issues we're going to be facing in the future with these electric vehicles? Higher battery voltages. This is the one that should keep every measurement person up at night. We have a large number of auto manufacturers globally who are announcing they're going from kind of this historic 400-volt battery to an 800-volt battery. And there's potential for these voltages to go even higher, especially in, medium to heavy sized trucks, in aerospace, in shipping. And this increase in voltage, it has safety issues, it has all these problems, but we're talking about EMI today. An increase in voltage is an increase in dV. And if we remember, my induced current equals capacitance times dV dt. A higher V means more EMC. If I double that voltage, I'm doubling that potential for interference. So this is a challenge that's coming. We're seeing this in a lot of different vehicles. The next one is if any of you have heard about wide bandgap switches in the inverters, these are silicon carbide, gallium nitride. These are going to higher frequencies. And it's not just that switching frequency that we worry about, it's the actual turn on and turn off time of the inverter switch. And this is just a diagram from an inverter switch where we can see the turn on time or the turn off time in this example is going from the switch is off to the switch is completely on. These switches are not perfect, they have a rise time. And if we look at the switches that were pretty commonplace 10 years ago, IGBT, we have a turn on time of 1,000 nanoseconds. And this is in the data sheets. This is a data sheet from a supplier where we have 3.4 volts per nanosecond. That's my DV. My DI, 8.7 amps per nanosecond. Well, silicon carbide is being made quite popular in the automotive inverters. These now have a turn-on time of 50 nanoseconds. That's 2 orders of magnitude less. We're having a dV/dt that's about 3 times more. Again, this is 3 times more potential for electromagnetic interference. And then we go to gallium nitride, which these are a little further out. These are more for smaller electronics right now, but they're coming. 6.3 nanoseconds, 200 volts per nanosecond dV/dt. That's 3 orders of magnitude more interference potential. So these are the things we have to start thinking about. And if we go back to our equations, because I don't want to make this a math problem. If we go back to the equations, we see that voltage equals L di dt. Higher battery voltages mean bigger dV. Faster switches mean a smaller dt. And the engineers are going to keep building these. We don't really have a whole lot of ability to change this as the test team. These power levels are increasing. This means more DI. And we can see these equations just explode. So what can we as test engineers help? We can help the inductance and the capacitance. We can eliminate parallel paths. We can eliminate loops of cable. Parallel paths, that's capacitance. Loops of cable, that's inductance. Distance between cables, we can control our test stand layout. So this is what we can control. We can also control some measurement techniques. So again, everything is more extreme. We need to mind the distances between our cables. For the same test lab, we might require more distance. Our shielding, our grounding, if something is done incorrectly or not quite right, we're going to have more currents traveling through these shields. This creates more potential for interference. This is really going to push the limits of what we've done. What worked before might not now. And high frequencies make old cabling routes problematic. So let's look at a test stand layout. I'm going to go through this briefly, but the short story is, if I have my device under test, my test motor, my load motor, my test inverter, I have my current measurements, my 3-phase current measurements. We want our power carriers and our measurement lines to really have as little parallel path as possible. If we can put them on separate sides of the room, that's best because we want them to be as far away as possible. Distance is important. We want to prevent power lines and signal lines from running in parallel. You don't want your CAN bus running right along your high current measurement. You don't want your measurement cables running along your high current measurement. And if these high frequency, high power lines and measurement lines must interact. You want them to cross at 90 degrees. It's kind of basic circuit level type layouts. We want to make cabling as short as possible, limit our inductance, limit our capacitance, avoid loops, create Faraday cages in our measurements, and really reevaluate your grounding. So try to keep things separate. Don't let things run in parallel. Keep them at a distance. Cabling. Cabling and measuring current is quite challenging. These power cables emit a significant amount of noise. We covered that. And the shields on these cables are quite important to their operation, actually. And the shields carry currents. And current sensors measure the sum of what's going through the current sensor. So my measured current, if in this setup where I have the shield going through the measurement, my measurement cable current plus my shield current is going to equal my measured. If I have 100 amps going this direction and 1 amp in the shield, I'm going to measure 99 amps. I'm going to get a bad measurement. So we have to look at how do we measure this? Well, the first step is to have a really good enclosure to protect the measurement from EMC. This is a way we can start to clean up our measurements. And inside my cabinet, I want to have my current sensor with the conductor going through it. And I actually want to route the shield around the measurement. This allows the inverter to be happy by having a good shielding and a quality measurement by having just the conductor going through the current sensor. The EMC cabinet will protect that measurement from the outside world EMC, and this is going to give us the best measurement possible. And ideally, we'd like to keep our AC and our DC signals separate. And that's what this will look like. We'll have the DC current going through my current sensor. We'll have a separate cabinet with my AC. My current sensor will be spaced appropriately. We have a really nice measurement. As far as cabling, we want to have these really nice shielded cables. Cables are expensive. Pay for the good cables. And really having a closed shielding path from the current sensor to an amplifier to the measurement system is going to help us a lot. And HBK offers a really nice path for that measurement. We offer a really nice Faraday cage around that measurement to, again, prevent those EMC, EMI issues. So use good cables, really look at your shielding and grounding path. And if possible, use a partner like HBK who can do a lot of this for you through the instrumentation. Sample rates and filtering. And as promised, I'm probably running a little behind, so I'm going to go through this quickly. I apologize. I have some questions I like to ask when people ask me about sample rates or filtering. What are you actually looking at? Are you looking at switching? Are you looking at a calculation like power? Are you looking at faults? What are you trying to measure? Again, are you looking at signals? Are you looking at calculations? And probably more importantly, what is the accuracy requirement? What is the bandwidth requirement? These are going to drive sampling rate. But more important than sampling rate is this filtering. And again, the question, why are we filtering? Are we filtering for anti-aliasing? Are we filtering to clean up the measurement from noise? And if this is the answer, we have to look at everything I just talked about, clean all of that up, and then we can start talking about filtering for noise. Because in electric power, we need that inverter measurement. We need that high frequency inverter. And are we filtering because we don't get values we expect from calculated channels? And the answer becomes calculated values are just taking in what is happening. The calculation, you can filter all you want. You're not changing the calculation. So we might need to use different calculations for power, RMS, reactive power, than we do for our sampling. And just looking at an inverter signal on the right, we can see, we have a signal at 50 kilohertz, 10 kilohertz in the fundamental, and we drastically alter that signal by filtering. So don't over filter. And we're going to share this, so I'm going to go through this without going through the detail. But we have other seminars on filtering, sample rate, and these details will be shared. And here's some practical knowledge that, again, we're going to share this presentation. But back to the noise reduction. Fiber optic measurements for reduced EMC. And if we remember, I showed this slide 10, 15 minutes ago, where we have all of these things affecting interference. And I raised the question, what if we eliminate copper paths? We eliminate capacitance, we eliminate inductance, we turn that conducted noise, that EMC, EMI, to zero because we've eliminated capacitance and inductance. How do we do this? Traditional power analyzer setup, we have a lot of cables, voltage cables. We have 8 current cables because we have a power supply in the middle. And these all have a potential for electric noise, or EMC, to pick up. We have test setups that look varying levels of poor, loops of cable, bad layouts, lots of noise potential. And we have dangerous voltages. We have these high voltages that are coming into the power room. We have loops of cable, lots of cables that can pick up this noise because they have inductance, because they have capacitance. Just another view, high voltage lines running in parallel to current lines, high voltage safety, EMC, because we have these long cable paths, we have that inductance, we have that capacitance, and we have these high frequencies coming from our device under test. So what if we made the measurement locally and then turned all those cables into fiber optic? So what HBK is coming out with is we're coming out with what we call a fiber optic probe. We have a probe that will sit right next to the measurement. Your measurement cable could be maybe 10, 20 centimeters. We digitize the measurement, bring it back fiber optically. No inductance, no capacitance, no possibility for conducted noise. So you're really limiting that pickup to that 10, 20 centimeters. Short cables, low noise potential. Same with current. We're actually integrating the power supply into our fiber optic probe so that we can amplify that current, digitize it, and send it back with no electrical noise potential. We're really minimizing that potential for the electric noise. What does this do? What does the fiber optic probe do for us? Well, it eliminates safety issues of those high voltages. You have no high voltages coming back to the measurement system. Minimizes EMC because we've turned our inductance and our capacitance to zero. Shorter cables prevent reflections. This allows us to go to higher sampling rates. Integrated CT power minimizes cabling. Again, lower chance for loops, lower chance for EMC, EMI issues. And lastly, we can distribute these at a very large distance. We can put them all over the control room, put them all over the test lab to reduce the amount of noise you pick up. So we go from this, all of these EMC, EMI issues, these multiple cabling routes, to this really clean setup where we have very short cables, very short distances, very low interaction, coming back fiber optically to the measurement system. Just some quick tech specs before I leave you. These will be able to measure up to 2 kilovolts directly. They'll be available in 2 or 20 megasample sample rates. And we will have that integrated power supply. And they're a small box that goes right next to the measurement. Everything's digital. Eliminate your EMC, eliminate your EMI. And just to recap, fiber optic lines minimize many of the EMC, EMI issues. We eliminate those long cables. We eliminate parallel paths. We reduce the inductance and capacitance of the measurement to a point so small we don't have to worry about that EMC, EMI. We let you operate in older or smaller test cells because you don't need that distance. And long story short, we can help you achieve better measurements.
Moving forward, let's move on to the second presentation of the day with Ranoji. Ranoji is an application engineer at HBK World, and he comes with a strong background in handling measured data and performing durability analysis and FE-based fatigue analysis. He has vast experience working in ENCODE software and handling the OEM requirements for various test data analysis and validation. And his session today will cover fatigue analysis, vibration testing, and reliability of EV components.
So hi everyone and welcome for today's topic and hope everyone is good. So welcome to today's webinar. So fatigue analysis and vibration testing and performance and efficiency of electric vehicles. So I am Ranoji Khochare. I am application engineer in HBK. So let's do the next topic. So here you can see the Princia. So Princia is the software side of the HBK. So under the ENCODE we are doing lot of things like durability analysis, processing the major test data, and for reliability point of view, if we see here, so let me take pen. Yeah, this one. So reliability point of view, we are having the ReliSwap tool. And apart from that, we are providing the trainings also. So during the training, you will learn like how to design for the reliability, how to design for the durability, and how to do the data analysis also. And also we are providing you the hands-on exercise also. And apart from that, when you are having some data and you don't have that knowledge how to do the analysis, so that time you can share the data with us, we can do the analysis and we can provide the result to you, right? So that comes under the engineering services. And also we can create SN and AN curves for that also, that comes under the engineering services, or fatigue or durability curve we can generate. So moving to the next. Yes, so here you can see the data collection chain, right? So if you see the physical phenomena, there are something you want to acquire or you want to measure. So here you can see this is the data collection chain, right? So here is the accelerometer. So number of sensors are there, right? Where you are testing the strain gauges or sensors are there. After that, you are using the data acquisition system. Then you are recording that. So here you can see the squiggly line like this. So after that, you are doing the analysis, right? And after that doing analysis, you can answer to your manager or you can discuss to your design engineer, okay, we are getting this much life, we are not happy with this, then again you are developing that product. So this is the data collection chain. So some customers are there or some managers are there, they are going with the only one chink of only one link of this, but some managers are there, higher level managers are there, they will take care of the whole process as the way to improve their product. So we have great message for those high level people, like HBK solution can empower the innovators, right? And in which domain we can concentrate. So like mechanical, so thermal durability means structural durability, reliability, and structural dynamics, vibration, and model analysis, number of things you can do. And apart from that, in electric domain we can do like performance, efficiency mapping, right? And thermal durability also, thermal management also we can do. So if you see what is our unique selling point, so from under one hood you are getting everything, like hardware to software, you have to just come up with the question, right? And answer will be there and solution will be there. So how to acquire and how to develop that product we'll see, but before that we'll see what are the challenges are there. Okay, so when you are developing any electric vehicle, so what are the challenges are there? And when we are able to quantify that, when we are able to measure that, then only we can rectify that or when we can solve that. So the challenges with the electric vehicle is, the first one is the battery tech going to crack, or the what are the electric vehicle you are using? The structure is the durable one. So that question will come in your mind, right? Suppose you are, and we have already seen number of EV companies are there. Their suspensions are breaking without giving any warning, without giving any notification, or we can say that. So that, I mean, we know that in Indians we don't easily trust on after watching the like videos. Okay, how much performance is there, whether it is durable or not, whether the vehicle is sturdy or not. So we can say like more publicity is there. Okay, this vehicle is sturdy or not. So to get that belief, first, we need to understand whether the virtual the predictions are correct or not. And the second question, the challenge will come, is this one. So electric vehicle range is good as what we have promised. Talking about this performance. So suppose you are traveling to Pune to Mumbai, right? And you stuck in Lonavala because of the bad battery range, and you having some battery issues like thermal issues. So when we know that, right? What are the challenges are there and how to rectify that, how to quantify that, right? So after knowing these challenges and how it is possible by using the encode, right? So we'll see how it is possible in encode, how to solve this. So to solve this, we are having today's agenda. So by using the encode, everything is possible. So for today's agenda, we'll see for durability point of view, what is the fatigue as a failure mode, and how we can calculate the durability of motor and the inverter like that. And we'll see some small demo for that. And when we're having a mission profile, suppose you want to see your vehicle will last long for 5 years or 1000 kilometer, right? You want to survive that. And when you are having the 100 or so data, it is not, we can say like, we can wait and we can check, okay, for this much hour how much time it is taken by that test. So instead of that, what we can do, we can accelerate that data, 100 hours data to 10 hours of data or 1 hour of data. So that comes under the accelerated vibration testing. And the second point is the electric efficiency, how to quantify that, power measurement and analysis. So we'll see the one by one. So what are the challenges are there? By using the encode, we have this agenda and we can provide the solution on that. So this is the product development cycle. Here you can see first we are doing some design, right? So CAD, CATIA models are there, right? And there we are doing some things, and after that design for a specific life, because we already learned in design like how to design factor of safety, how much we have to give. But why uh, fatigue is important? Because we know that already we have learned, right? When there is a ultimate strength is there, breaking point is there, then accordingly we are considering the breaking point, and then part is failing, then factor of safety comes into factor. But the fatigue, the factor like when there is a load we are applying which is less than the yield strength, and then also parts are failing, right? So that's why the durability is very important. And when we see, this is the map, like product development map. Here we are creating one product, right? And then we are checking virtually how much life we are getting, right? And after that we are just checking, cross checking, like okay, when we are keeping this prototype on checker table, whether we are getting the same life or not, at the same element or at the same node we are getting life or damage or not, right? So indirectly we are doing the qualification or validation, we can say. And after checking the number of samples, how many life we are getting, okay, whether it is reliable or reliable or not, so we can calculate the warranty analysis we can do. So that part comes under the reliability. We will discuss it another time, but today we'll focus on the prediction of the durability, because you cannot watch your product is failing, right? And it is time consuming and money wasting also. So instead of that, instead of watching the prototype is failing, you can do the virtual analysis. So at same layer or where you are getting the hotspot, right? So how the product is failing, virtually you can do the calculation, and you can calculate the life, and accordingly you can discuss again with your test engineer or your design engineer. Okay, I want 3 years life, and here I am getting 2 years life. Now again you want to improve, or you can optimize that design. So that's why the prediction of durability is very important. So yeah, we'll go through this durability first. So talking about the durability here. So if you see here, here is the coupon is there. We are saying keeping these samples here, and we are checking. Okay. So why durability is important? Because we are talking about the electric vehicles, and electric vehicles is not just about the electric performance, range, and all that. Because finally it is the mechanical structure, and when we know that we are getting from that structure this much life, or it will survive for this much, that's why durability is important. Because we know that 90 to 80% parts are failing in automobile because of the durability and because of the damage only. Now if you see here, yeah, so here you can see the crack. So as per the definition of the fatigue, right, when you are applying the small loadings and reversal loads you are applying without creating a like ultimate strength, that much loading, or breaking point, that much loading, because of small loading also part is failing, right? So it will create first crack, then crack will propagate, right, and then part will fail in two parts like this. So for that what we are doing, we are keeping the coupons and we are checking, okay, when it is failing, right? So for that when that part, or the sorry, the coupons is filling, so that time what is the stress range, right, and how much cycle it is surviving. Accordingly, for that number of specimens, we are creating a plot, creating a log scale, and we are creating a SN and EN curves, and from this SN and EN curves we are calculating the life, right? And how we are implementing and how we are using this in encode, we'll see that. So this is the fatigue analysis roadmap. Now we know that what is the fatigue, why this is important, right? But how encode is utilizing this and how we are calculating this the life, right? So here is the 5 box tricks. So first one is the loading. So what are the data you are recording? So we have already seen data connection link is there, right? So we are recording the data and then measuring that. Then we are doing data acquisition. Then suppose there are anomalies or something is there. Then we are cleaning that data, and that data we can use for the post processing to calculate the life. So that data you can see like here, right, like a squiggly lines like this. So this is the loading. You can give the time series loading also, you can give the PSD loading also, that is also possible. So we are giving 3 inputs, right? First one is the loading, second is the FE model. So when we talk about the FE model, like design life, we can do this, and then we can calculate the fatigue and damage. So this is the FE model, right? So in FE model, what we are doing, so we are having number of pre-processing software, right? So there we are solving for the stress range, and we are getting at a particular node or element, right? What is the stress tensor and the stress range is there, right? Now we are having a hypermesh, abacus, nanstam, lsdm, number of pre-processing softwares there. So that software output file we are importing in encode. So this will be input file to encode. So second is the geometry we are providing to encode, and we already seen, right, how to create SN and EN curves or fatigue curves. So suppose this is the material or this product is made up from aluminum steel. So that material we are assigning here, right? So after giving these three inputs to three fatigue analysis glyph, so encode is checking, okay, when we are giving this much loading at this node, this much stress is there, then how much cycle it will survive, right? So accordingly, we are getting the light, and it is suppose this is a component when crack is initiated in automobile industry, we are seeing the part is filling. So in that test engineer or that engineer will understand that, okay, we are interested in 3 years life, we are getting 2 years life, because some companies are there in the market, they are just earning the revenue for just from selling the spare parts. I'm not taking the name, but some companies are there. So why durability is important? Because you have to create a optimum product or design such a way that even if you're putting too much factor of safety, again because of the self weight, the product can break. Okay, so you have to create a product such a way that it will last long for the desired or required life only, right? That's why the reliability is very important. Now I will show the one small demo here, and again, sorry, yeah. So here you can see the demo. So left hand side you can see. Hope everyone can see because I'm not here to.
Yeah, it's
Yeah,
visible.
is visible, right? Encode screen is visible, right? So under the encode there are 3 4 modules, right? The glypher is there. Hope everyone can see my screen and my cursor. So glypher is the module we are using to do the data analysis and signal processing. We are using this, right? And in glypher also, when you are having the string simple data, from that also you can directly calculate the life and damage. But when we are having the design like this FA tool, like this FA model like this, right? So here you can see. So here we already solved the stress model. So in this we can see that we are having the stress model. But what to do with this, right? We are having the stress model. But you can know that, okay, at this node you are having this much stress is good. But after just knowing the stress, we cannot predict or we cannot do anything, right? So why, that's why the encode is very important. So after knowing this, right? So this much stress or something is there. When we are assigning this loading, right? So here I am giving the PSD loading. So at this frequency, this much amplitude or G value is there, or this frequency, this much is there. So you can provide or you can give input in time series domain also, frequency domain also, a number of things you can do. And suppose vibration, or suppose you are doing the analysis of radiator, right? So thermal loading also you can give, vibration also you can give. So combined loading also you can give here. So I am running this flow. So here you can see, right? So at node 957, right? So I am getting the life equal to 12.86, right? So roughly we can say 13 hours, because I have given duration for that PSD and mentioned that duration in encode, like 1 hour PSD we are giving. So it is surviving at this node for 13 hours, we can say. But we are interested, okay, we want to survive this battery packet for 20 hours or something more than that, then again you can redesign that. So in this way you can redesign your product, again you can discuss your team, and you will get the nice life. So let me share my screen again. So here we understood, like, okay, so kitne saal chalegi means how many years. Okay, sorry. Okay, kitne saal chalegi means how many years we will get that life. Okay, how many years it will survive, right? So this is the battery brackets, you can see this is holding this battery pack, right? So depending upon your requirement and number of components are there, you can do the body in white, the whole damage calculation of entire vehicles also you can do. So that much easy and useful thing is there. By using the design like you can achieve this. Okay, and moving to the next. Now again, after knowing this, how to calculate the life virtually, because we cannot wait there and how the product is feeling. So at least to get some confidence, right? Again, we are creating a prototype and we are keeping that in checker table, right? And we are checking whatever the life we are getting at that same node when we are solving on the virtually, right? Same life we are getting or not when we are doing sync and when we are giving this excitation on this shaker table, right? So you can do the correlation also, that is also possible. And when you are having the mission profile, right, and whether that component or that what we say prototype is meeting that target life or not. So for that we are going with the shaker table, and for shaker table we can create a vibration profile design. And how to create that, we'll see. Now if you see here, this is the vehicle, and your customer is thinking, okay, or means the manufacturer is thinking, okay, it should be survive for almost 5 years, or it should run like without getting any damage for 1 lakh kilometer or something. So let me take brain. Yeah, 1 lakh, or that is the mission profile, or we can say the duty cycle. But every time it is not possible how the vehicle is running, what are the bumps or something, or what you are getting, and you cannot always paste the strain gauges and all the values to get that data. So instead of that, what you can do, you can create a mission profile like this 1 lakh kilometer you want to perform without breaking this any component of this vehicle. So directly you can convert into this. So this is the pavement track, city track is there, Belgium bump track is there. So directly this damage we are considering like this, and from this we can multiply this and we can create a duty cycle. So when this vehicle is running for 5 years, definitely same damage we are getting from these tracks also. Now after that, what we are doing, so from this we are getting the data like this, right? This is we are getting the time series data. Now this is the mission profile. Now whatever the mission profile is there, when there is 1 lakh kilometer that vehicle is in, same data we are getting from this tracks also. Now the question is how to reduce this, because suppose this data is 100 hours data is there, right? But 100 hours data we cannot give to the shaker tables, right? Because it is time taking, and it will we have to put too much money, right? So here you can see the variety is there, and the same damage what are the we are getting, same damage and same excitation we can give to this shaker table. And depending upon the actuator, electromagnetic or pneumatic and hydraulics, the capacity or capability of the shaker table is we can say we can give that PSD in that format. So after knowing the capability of the shaker table, here we can see now this is 100 hours of data. We can accelerate that to 10 hours of data, keeping the same damage. So we can say that when we are giving 10 hours of data, definitely it should survive, or it will survive for 100 hours. Sorry, 1 lakh kilometer. When we are running the vehicle, it will survive. So when we are accelerating this data, here you can see indirectly we are creating a PSD such way that we are creating or we are increasing the G level, right? And again we can create that maximum profile design, and we can provide and we can give that as an input to the shaker table, and we'll get the same damage. So directly we are validating what are the product or what are the components are there, we are getting the same damage or life or not. And when it is failing, then we can say that again we have to redesign that. So without predict means early stage we are predicting this, right? So that's why input glypher this vibration profile design is very useful. And because of the time constraints, I'm not showing again the demo, but here we can see how to create a flow. So here you can see when the major data is there, like too much 100 hours of data is there. So here by using this 10 synthesis glyph, you can compress that to 10 hours also, right? So for that, when there is a time series data, we can use the frequency response function, right? And when we are having the page data, we can use the ERS also. So from here you can see we are getting the damage number, right? And after the 10 synthesis, we are getting the G value here, the PSD here we can give, and this PSD we are giving to the shaker table. So in this way we are accelerating the data. So you can see this. So we are saving time, money, keeping the same damage. Now moving to the second point, second topic, efficiency analysis. When we know that how to quantify the motor efficiency and how to measure that analysis, then only we can provide some solution. And before that, we'll see first e-drive system is there. So we can measure the samples like 2 mega samples per second. So already Mitch has explained these things. Okay, this is the battery pack, right? And here we can measure that thing after the inverter. So here we can measure the current and voltages, and after that we are converting that into the mechanical engineer mechanical energy. So here we can measure the speed and torque also, right? And after that we are acquiring the data over here, and here the input plays very important role. So after having that data, what to do with to do this, right? So when the data is flowing or energy is flowing, there are losses, right? And how to quantify that? So for that we'll see how the energy flow is take place, and from that how to calculate the efficiency, and after calculating that efficiency, how to change the set and everything we'll see in next slide. So here you can see DC current or DC currents are here. We can see the battery pack, the energy is there, and then we are converting that into the alternating current. Then again we are converting into the mechanical. And when the data is flow, sorry, the energy is flowing from here to here, definitely there are losses are there. And how to quantify that? Because we know that when we measure the power flow like DC current and voltages, like three phase of AC current voltages, and finally we measure the mechanical speed and torque. From that we definitely calculate the power also, right? But to calculate the efficiency throughout a quantifying the efficiency, how to calculate, and by using the encode, we see that. And for that we are having electric glyph, very nice glyph we are having. So from that we can calculate the efficiency of the inverter, the battery, and the motor. So this is the flow what we can create for that. And why we are interested to calculate the efficiency, everything. We know that we are facing the range challenge, that's why we are here. But to calculate the alternating current, the what are the inverter energy there, and how we are transferring that to mechanical, to measure this, right, and quantify this is the very difficult, right? And why this is difficult, we'll see. So if you see, when we're having the battery power, like we can directly calculate, right? Power is equal to I into V, current and voltages we can calculate, and we can calculate the mechanical power also, right? Torque into the speed, right? But when we see the alternating current, when we are converting that, so here you can see the electric inverter, digital power inverter, what are the current and voltage we are getting. So current we are getting in the form of multi-phase, non-sinusoidal, and varying amplitude and frequency we are getting, right? And when we see AC power calculation can be hard because there is a phase difference between the voltage and current, and that causes the losses. And that causing the loss means that causes are happening because of the phase lag or phase lead, because of the inductors and capacitors, and periodically the energy flow is reversed. So that's why what is the active energy, what is the reactive energy, and what is the apparent energy, that is the important. So active power is the dissipated in the circuit, and that does the meaningful work. And the reactive power is the out of the phase introduced back into the system, and that causes the losses. And when we are able to quantify what is the reactive power is there, then only we can calculate the efficiency. So for that we are having a simple drink analogy, we'll see that also. So if you see, this is the apparent power, right? Like this is the coffee mug is there or coffee cup is there, so this much you can see, but from this you can consume only this much only. Now you can see like this, so 80% you can consume. But when you know that okay, 20% is the foam or 20% is the reactive power in the reactive power there, then only you can say that okay, 80% actual efficiency we are getting. Yeah, this is the active for it. What is the total battery energy what you are having, from that you can use that actually. And this is the reactive power that you cannot use or you cannot consume this, right? And this is some equations are there, so no need to worry about this because encode is taking care of all these things. So here we are here. Why we are here? Because what is the capability and what are the challenges are there, that we can solve that, right? So apart from this, how to do this, how we are calculating, so for that you can drop me mail, we can discuss on that on team also, that is possible. But now we'll see when we are getting the inverter output, right, like this current and voltages, right? So here you can see by multiplying this we are getting the power, but here you can see here we are getting the negative or reactive power, you can see. And why we are getting this? Because the fundamental control frequency, when there is a low frequency is there, that we are getting. And at high frequency we can say because of the switching harmonics from digital inverter, that high harmonics much larger in the voltage than the current, and this high frequency make the power calculation very difficult. But encode, we are taking care of all these things, and we are getting the performance wise efficiency of the power for the motor and everything. Now if you see here, this is the demo, or we can say this is the how we can do the analysis in encode. So here I already given this input in AC current voltages, then I have used this filtration, then electric power glyph is here. So if you see at this torque, when the torque is this much, and when the shaft rotation of that motor is this much, so we are getting this much efficiency. So how torque is increasing and shaft speed also increasing, right? So we are getting the maximum efficiency. So in this way we can compare the efficiency map and what is the old and new motor is giving, and we can find out where we need to change or whether the change in design or any strategy that we can build, right? So from this we can understand, okay, kitna dekhi means how much mileage we will get after knowing what is the and we will get that when we know that where this much losses are there and how to quantify this, right? And if you see here, the encode software can help you. So coming to the conclusion, will help you to meet the both requirement. First one is the durability. So durability we already seen how to calculate the life and how to predict that life, right? From for the EV to create that a durable product. And for performance point of view and efficiency point of view, we have seen the electric grip also, right? So here we can see we have achieved the target like kitna degi means how much mileage we will get, and for structural point of view, to structural durability point of view, right? How much year it will last long, right? So this is the end of the slide. So, and thank you everyone. This is my mail ID ranoji.khochare@hbkworld.com, and we are in this industry from almost 40 years. So from start to end, you will get means everything. You have to just come up with the questions, and solution will be there. And apart from this, you can see these links. So you can go through this for webinars, electrification links are there, and virtual days seminars are available. And here we'll see the question and answer.